Okay, any questions about electrophilic addition or anything else? No. Okay, so the last overall topic that we will go through, and we'll do it today, next Wednesday, and then maybe a little on Friday if there's leftover, is free radical halogenation. So the schedule is today we'll do today we're going to start free radical halogenation. Friday will be questions about the exam, and at the end of class I'll take your list of topics, and I will create one tonight and send it out or post it online, and then you can have yours back on Friday if you need it earlier. Take a picture of it before you turn it in. Annie?
So I do have a question about like the electrophilic. So some of the mechanisms, do you want transition states, or would you say that you want the ones that you specifically want transition states for, or is it more you just want the intermediate?
I can tell you what I don't want transition states for, and that's going to be anything with a triangle. Okay. So the bromonium ion, any mechanism with bromonium ion, the transition states are going to be really difficult because we don't know where the triangle dotted lines start and end with the dotted lines of the transition state. But if it's something as simple as like HBr addition, then I would want transition states. I would want them. Would positively want them, yes. The only ones that I think would be no would be the bromonium ions. So I can't tell you, because it's probably switched from year to year on the older exams, whether I've asked for transition states in those reactions or not. So it may be 1 year I did, 1 year I didn't. But one thing I never do is ask for them with the bromonium ion.
Do you also want us to show the delta positive for like intermediate within the triangle? Or do you just
for the intermediates, you can show the delta positive is the charge. So when you're writing your transition state, the delta positives that go on the carbon, let's say something like this, the delta positives that go on the carbon are the charges. So instead of there being a +1 charge that you would write, the delta positives are necessary.
So this is what you would want to be shown.
Yeah. So specifically, we would start. Let's say specifically, I would start with so you would take this pair of electrons, use it to bond the bromine, and then the arrows would look like that to form the bromonium ion. Then let's say the other Br minus would come in, add to that carbon, and the arrows would look like that, moving over the bromine. And then, so then in the final product, what I'm looking for is the fact that the bromine that added and the bromine that was there to begin with would be trans with the stereochemistry. So that would be a complete mechanism for Br2 addition to any double bond. These three steps would be the mechanism.
So you just don't want us to show the transition state.
Right. Right, just the intermediate.
So the second thing is the intermediate?
Yeah, that's the intermediate. The bromonium ion is an intermediate. because it has a charge. It's just a split up between those two carbons.
Would it be possible to practice the mechanism real quick for the HBr and H2O2?
Sure, because that's going to lead us into the free radical for today. So if I was to ask you, and I have in the past, to write the mechanism to take an alkene, and let's say that alkene plus HBr, H2O2, and write the mechanism, the first step is going to be to take the peroxide and cleave the oxygen-oxygen single bond with two half arrows. That's going to give you a transition state where I'm breaking the oxygen-oxygen bond. So in this case, I would ask you to write the transition state. So I'm breaking that OO bond, and I'm basically going to end up then with two oxygens that each have their unpaired electron. So I'm breaking the single bond, and I'm giving each oxygen its electron back. Okay. So that would be step one. And today, well, we called this an initiation step, I believe, last week or the week before. And so today, when I make my radicals, or when I make my atoms with unpaired electrons, that's going to be an initiation step as well. So then the second step of this mechanism was to have one of the hydroxyl radicals react with HBr. And so in that case, I was going to break I'm breaking the HBr bond. I'm taking the unpaired electron that would go with the hydrogen. I'm going to pair it up with the unpaired electron of the oxygen, and then move the unpaired electron, give the unpaired electron back to the Br. So what's happening is the OH dot is coming in and taking a hydrogen atom from HBr. So the transition state for that is I'm forming the OH bond, and I am breaking the HBr bond. And again, notice in these transition states there are no charges, because there are no charges in a free radical mechanism. And then I would end up making water and a Br dot, which you could call a Br atom, or you could call it a Br radical. It is technically just a Br atom. So these two steps set up the critical part for the mechanism. And so the next step in the mechanism would be to add the Br dot to the carbon-carbon double bond. And if it's me, I'm going to do something here that you're not going to like, but I'm going to erase the Br. Because I can easily. And I'm going to put the Br dot over there. Because then what I'm going to do is I'm going to break the carbon-carbon bond, and I'm going to pair up the carbon on the right's unpaired electron with the Br dot, and then the other unpaired electron is going to go to the tertiary carbon. So my arrows are going to look like that. And then I'm going to end up with my transition state here. I'm going to end up forming a carbon-bromine bond and breaking the carbon-carbon double bond so that the transition state would look like that. The Br carbon-bromine bond is partially formed, and the dotted line then for breaking the double bond, which then gives me, as my final product of that step, the Br added to the carbon on the right, forming a tertiary radical on the left carbon, which is the more stable radical. So given a choice here, I'm going to add the Br to the right carbon because that will give me a tertiary radical. If I added the Br to the left carbon, it would give me a secondary radical. And so that would be the radical that's formed in that case. Okay. Right. So far we've got 3 steps. And then the 4th step is going to be to have that carbon radical react with HBr again, so that that carbon dot can pull the hydrogen off of the HBr and complete the final product. So that's going to be to take this radical, and I don't know, I like to have the molecules close together as opposed to drawing an arrow halfway across the page. I can grade either one more easily than the other, but one of the things I like to do is I like to just line them up. So that, for instance, if I'm going to break that HBr bond, I'm going to pair up those 2 unpaired electrons and then give the bromine back its unpaired electron. So that in that final transition state, it's going to have a carbon hydrogen partial bond, hydrogen bromine partial bond for what's being broken, and then the right side of the molecule stays the same. And then the final product will have the H added to the carbon with the most substituents, the Br added to the carbon with the most hydrogens, anti-Markovnikov, opposite of what Markovnikov is. And then there would be another Br dot that would then cycle back in and continue the process. So that would be the 4 steps. And we would leave it at that.
Could you explain what happened in the 3rd step and what's next?
So what happened in the 3rd step was the bromine, I'm going to split the double bond apart. And one of those 2 carbons then is going to use its unpaired electron to bond the bromine. If I do it the way I did it, I just formed a tertiary radical. If I would have done it the other way, let's say I would have added the bromine here, then the radical would have been on that carbon, which would have formed a secondary radical. Which radical is more stable? The tertiary one, and so that's why I get this radical as opposed to the other one. And the reality is I would get some secondary as well. This reaction is not going to be 100-0. It's going to be more tertiary radical formed than secondary. So the issue here is, why does this reaction go anti-Markovnikov? Number 1, it's a different mechanism. Number 2, I'm adding something different to the double bond. In Markovnikov addition, I am always adding a plus charge to the double bond. And so the plus charge has to go on the carbon to give you the most stable carbocation, which means the plus charge species always has to go on the carbon that has the most hydrogens, because by definition, the carbocation is going to be the one that is most substituted and therefore have the less hydrogens. So with an addition of an electrophile, it goes Markovnikov, but for a radical, since I'm changing what I'm adding, it's going to change the regiochemistry. So that's why it's changing the regioselectivity. So that would be the 4 steps that I would write for that mechanism. And typically what I would ask is I would ask you to write the mechanism for formation of the major product. So if you got stuck on the mechanism, you could always write the major product down and get some points. But that's the 4 steps that you would write for that.
So you don't want us to do like any termination steps at all for it?
So this one, we didn't do any termination steps. So for this one there, and this is kind of unusual because what happens is in the old book, we would have done free radical halogenation before we did this reaction. So we wouldn't have known about termination steps. And when we did this 2 weeks ago, I didn't say anything about termination steps because we weren't concerned. We just said, oh, the reaction ends when it runs out of stuff, which is exactly what happens. But for free radical halogenation, we are going to have termination steps. So these 4 would be the 4 I would ask you for this mechanism.
And basically, because it's gonna be the same things being added, like this is exactly what we would write on the test, right? There wouldn't be any other, aside from the fact that maybe it would be a slightly different alkene.
Sure. And all I would do if I knew how to do this was I would change the alkene. The first 2 steps aren't going to change. This 3rd step is only going to change simply because it's going to be another alkene. You know, and so that would be, I mean, yeah, it's essentially the same mechanism. But then again, they're all kind of the same mechanisms, to be honest. Right? I mean, you're adding HBr, you're adding an H plus to a double bond to form the more stable carbocation. Then you're adding the Br minus to the carbocation. So they're all very similar. But this is where, as you're going through and sort of learning this, as opposed to just memorizing what steps are there, you can take it to the next level, which we all would love for every student to do in every class, is, you know, beyond just memorizing what you need to do, why am I doing that? And so in the first step, I need a radical. So how am I forming that radical? By splitting apart the peroxide. If I just added HBr, it's not a radical mechanism because there's nothing there to form a radical. Second step, I need the Br dot to add to the double bond. So the second step gives me the Br dot. And then the third step, okay, the Br dot has a choice. What carbon is it going to add to? And so it's going to add to the one to make the more stable carbocation. And then for the final step, I need my product. So my radical is going to go ahead and grab a hydrogen. I could probably grab a hydrogen from a water. But if it grabs a hydrogen from a bromine or from an HBr, then it just starts the process all over again. If it grabbed it from a water, then the OH dot's going to grab another one from the HBr, and it's just going to continue. So every step has a purpose. And if you, as you're going through, kind of remembering the purpose, that may help you if you get stuck. But you're also going to need to know, well, what am I adding? I'm adding HBr, anti-Markovnikov, 50-50. You will not get the table that I gave you on Monday. There should be no, because you weren't going to get that table anyway. Right? You're not going to get that table in the future when you're taking in whatever AT test you want to take, whether it's DAT, whatever, pharmacy at, medical at, optometry at. They will not give you that chart. So, I mean, you're not getting the chart. So hopefully transfer the chart here. But don't just I mean, there are certain parts that you want to be able to know. You know, KMNO4 and base, what am I adding? 2 OHs? Neither? 100% cis. So whatever way you get that from the paper to here, flashcards, people drilling you, you know, I could bring in one of my former students one time who was telling because when they're in the lab and I'm there, it's like I'm not even there. They're just, it's all sorts of stuff I hear. And I hear it. Sometimes I ignore it, sometimes I don't. And one of my students was like, she goes, you have to be thinking about this all the time. You're at a stop sign or a stoplight, think about organic. That was her motivational speech. I don't know how well it went, but that was, as you're going through it, you want to make just whatever way you can, you have to remember those. Yeah.
So the H plus and H2O and like ROH, are you just going to say H plus or are you going to give H2SO4?
I'm going to give you H plus in either water or H plus in alcohol.
Okay.
I'm going to give you mercury in water or mercury in alcohol.
So you're going to give like one on you.
I'm going to give you the reagents that are in the chart, yes. And I will give them to you in that form. And I will give you no other reagents than that, I don't think. And with those, we're getting towards the end of the semester. What's the difference between how HOH reacts and ROH? They're almost identical in the way they react. One, you're going to add an OH. The other one, you're going to add an OR. So they're very similar. I mean, through all of this, I've tried to give you, some just general big ideas here that you can use that will help you if you get stuck. Or help you if you see something that you hadn't quite seen before. Because people are always like, I don't know where you pulled that out of. Like, there's 10 years worth of exams. My creativity is shot at this point. And I only say that because it's a challenge then to try and find something that I haven't asked before. Not to say that you should memorize all the exams, because if you do that, it's not going to end well. It really isn't. You're using those as practice problems, or use them as practice exams. Yeah, I would say last year's and the year before that and the year before that. I think it's been 6 years since I flipped. So before, some of this stuff would have actually been in second semester, which might be why there's some second semester exams in the exam 3, because it used to be the first test of second semester was the killer test. If you're reading between the lines, that would be this test, this killer test. But is it really the killer test? I mean, there's a lot of stuff here to organize. But that's the thing, you just have to organize it. Organize it and see the similarities. Okay. All right. Everybody okay with everybody okay with that? Because now what we've done is we've gone off on a tangent in study skills, and I guess the only thing I'm lacking is telling you how poor you're going to do. And that would be another class. But anyway, that's how you want to approach it. I'll erase that part of the tape. But that's why I gave you the chart was to kind of show you how you could organize things. So if that works, fine. If it doesn't, I think somebody asked me this morning, could I rearrange things? Yeah, you can rearrange things. The flow chart is just kind of there. If you use the flow chart a number of times, hopefully you don't need a flow chart anymore. Right. So it's just kind of a systematic way of going through that. Okay. So what would be different about the mechanism for free radical? Well, number one, if we're talking about free radical halogenation, and this is in chapter 18. I don't know why it's in chapter 18, but it is. For the free radical halogenation, the essential elements are that what I'm going to do is I'm going to take an alkane and I'm going to react it with a halogen. I'll take Cl2 or Br2. Those are the two that I'm going to use. And the reaction requires light or heat, and we'll get into the reasons for that next week. But the light or heat's necessary for this reaction to go. The differences between them, we will get into next week. There are differences. So what's going to happen is this. I'm going to substitute a carbon-hydrogen bond with a carbon-halogen bond. So I'm going to take one of the halogens here, and I'm going to substitute it for a hydrogen in my alkane. So I'm going to end up forming then either CH3, CH2 with a Cl, or if I'm doing this with Br, I'm going to put a Br there. And then I'm going to end up with an HCl or an HBr because there's another bromine or chlorine atom and the hydrogen that came off the alkane. So in a way, this is kind of a double substitution reaction where I'm substituting a hydrogen for one of the halogens and a halogen for one of the hydrogens in the alkane. Now, the big picture of this is, why does this matter? And why is it in first semester and shouldn't be in chapter 18? And the reason for that is this. Alkanes are great molecules. They're readily available. All you got to do is just get some crude oil and you have plenty of alkanes. All right, they might be long. They might be 18, 20, 30 carbons long. If they're like 50 carbons long, they're going to end up on the road because that's what the road's made of, is asphalt, which is carbon chains of 50 or more, give or take. But alkanes are important from the fact that if you drove, you got here using alkanes, unless you have some super Tesla vehicle. But even then, you got your electricity probably from a carbon-based source, unless you have your own solar power plant at your house, which we don't have yet, although if you're affording a Tesla, you might have that available. But if you're burning a fossil fuel, you are burning carbon. So alkanes come from crude oil, and that you can do two things with them. Number one, you can burn them, which is important. Okay, it may be evil in today's society, but it is necessary. And so you burn them by adding oxygen to them and combusting them to CO2 and water. Important reaction, not helpful if I'm trying to build bigger molecules, which is what synthetic chemists try and do. On the other hand, free radical halogenation, which is the other thing I can do with these, gives me a halogen attached to my alkane, and now what can I do with that molecule? Well, that's exam 2 and 3, right? I can do eliminations to form double bonds. I can substitute it with an OH or an OR. And I can do all those reactions with the alkyl halide to turn it into something else. And next semester, we'll find out that you can do even more things with alkyl halides. So from a big picture viewpoint here, alkanes are great building blocks for complicated molecules, but you can't burn them. You have to put a halogen on them. And so free radical halogenation is the way that we do that. Okay, so that's how we make the alkyl halides that then we can do other things with. As far as the mechanism goes, we're only going to write the mechanism for replacing one hydrogen with one halogen. So that's monochlorination or monobromination. Right? What are our steps? Our steps are going to be, we need an initiation step. I need to make a radical. How am I going to do that? Well, in the reaction that we just did, we split apart two O's. In this case, what I'm going to do is I'm going to take my chlorine under the influence of the light and the heat. I'm going to end up splitting those two chlorines apart, each chlorine getting an unpaired electron. Transition state will be chlorine-chlorine bond being broken, and I will then end up with two chlorine atoms. Now, the critical part of this is I don't need all the chlorine molecules to break apart, and I'm not going to get them. So if I hit this with light or heat, I'm never going to break all the chlorines apart. All I need is one. In the peroxide mechanism that we just did, all I needed was one peroxide to break apart. Because every time that peroxide reacted, what happened? It made another molecule with an unpaired electron. And what happened with that unpaired electron species? It reacted to give another one. So the process can continue on in a cycle as long as you get one radical. So I'm ahead of the game because I have two.
Did you say this happened because of light or heat?
Yeah, so this will happen either with light or with heat. That's the purpose of the light and the heat, is to break the chlorine or bromine apart. So this is initiation. The second and third steps are going to be propagation. So in the propagation steps, I'm going to propagate the species, meaning every time an unpaired electron species react, another one's formed to go back into the cycle. So my Cl dot is now going to go ahead and it's going to pull off a hydrogen atom from the ethane in this case. So the carbon-hydrogen bond is going to break. The chlorine dot's going to pair up with the H dot, and the other electron in the bond is going to go to CH2. As far as my transition state goes, and again, I like to draw the transition, I like to have the reactions occur the atoms next to each other, because it makes the transition state much easier to draw. So I'm breaking a carbon-hydrogen bond, I'm forming a carbon-chlorine, or a hydrogen-chlorine bond. So there's my transition state. And then in the end, what's going to happen? I'm going to form HCl, keep it in the same order. I'm going to form a HCl bond, and I'm going to end up with a CH2 with a dot of my ethyl. So now I'm going to form my ethyl radical. For writing a mechanism, I will tell you sort of what the product you're supposed to write is. In this case, it doesn't matter any of the 6 hydrogens I remove in ethane, I'm going to get the same product. I'm always going to get one chloroethane. Okay. That's a primary radical. I'm not concerned. Because remember, primary radicals they're not as stable as secondary, they're not as stable as tertiary, but there is no prohibition against writing primary radicals because they can form. Primary carbocations, you're still not allowed to write primary carbocations. Mary?
Why under propagation is it CH2 on the right side of that molecule?
Because, it's not. It's supposed to be CH3. It's supposed to be CH3 there. And I don't know. I like to add the two. I like to add it from the left side. You could add it from the right side. I just like to see the things close together so the arrows don't go halfway across the paper, because when the farther the arrows got to go, the more likely they are to not go in the right place. So when things are close together, it's usually a quick. And notice all these arrows are half arrows. Okay. So that's propagation step 1. I have now formed my ethyl radical. And what I'm going to do, I will tell you ahead of time, I'm going to rotate the ethyl radical so it's there. So that then what I can do is that ethyl radical needs to form the product. And so what's it going to react with? It's going to react with chlorine that did not dissociate. Now remember in step 1 I said, you don't need all the chlorine to dissociate, nor is all the chlorine going to dissociate. So there are more Cl2 molecules intact than there ever will be Cl dots. Okay. So when we think about reactions, we tend to think that every molecule is doing this. It's not. So just one chlorine dissociates. So I'm going to break apart the chlorine-chlorine bond. I'm going to go ahead and pair up the CH2 dot with the Cl dot that would result. My transition state is going to be forming partial carbon-chlorine bond, breaking chlorine-chlorine bond. To now get to the final product, which is ethyl chloride, and I just made another Cl dot. And what's that Cl dot going to do? It's going to go back into the reaction and take a hydrogen off of another radical. And I usually don't write that. I remember when I taught this stuff down at OU, apparently the person that came before me did draw the circle and put it back into the cycle. And they were like, there's arrows going everywhere. I have no idea what's going on. So I didn't cycle it back so that they weren't confused. But that's what happens. This is the problem with radicals. Once you get rid of one, another one is produced. And so they just continue on until, in the last reaction, we just said, run out of stuff. In this case, we're going to be a little more specific. Until we terminate them, or they terminate themselves. So termination steps are going to be what causes the radicals to be gone. I have two radicals. I got a Cl dot and an ethyl dot, so A and B. So 3 termination steps, A plus A plus B, B plus B. That's what the termination steps are all about. So first thing, 2 chlorine atoms are close together. They decide to go back. We're going to form a chlorine-chlorine bond, and we're going to end up with chlorine. If you're having a sense of deja vu about that reaction, that is the opposite of the initiation step. Same transition state. How about a Cl dot and a CH2 dot? Well, minus 10. Forgot to put my arrows in. It's the dots to dots. But the arrows are in the same general direction. But it's the dots that are pairing up. Okay, Cl dot plus ethyl dot. Again, forming the partial carbon-chlorine bond is my transition state. And then forming the carbon-chlorine bond for sure, for good. And then my product. Now, far more product is going to come from propagation step number 2 than this termination step. Because what you have to realize is all these termination steps are just these radicals floating around solution. And when they come, or in the gas phase, these radicals are floating around. When 2 radicals get together, if I guess in the right orientation, they'll couple and they'll form the carbon-carbon, or the bond. More than likely, that Cl dot's going to come in contact with another ethane molecule, and rip its hydrogen off. So this is just forming a small amount of product. Now, if I was proposing that this mechanism was really happening, I would have the burden of proof. Since I have made a CH3CH2 dot, I would have the burden of proof to show that two CH2 dots could come together. This is technically what is called a coupling reaction. Whenever two radicals share up or share their unpaired electrons. And so now in this case, I'm forming my carbon-carbon bond, and I guess I forgot the transition state. The transition state would simply have dotted lines between the carbons. So if I'm proposing this mechanism, someone's going to say, if your mechanism is true, show me that you're making butane as a product. And so, of course, that's not the way it works. The way it works is people looked at the products and said, hey, there's butane in there. Where did it come from? And then proposed a mechanism that accounted for the fact that butane is being formed. Kaylee?
So does that mean the CO would also be coupling again?
Yeah, I mean, coupling is whenever two unpaired electron species meet. So all the termination steps are coupling, but technically it's really when two alkyl radicals react. Like, we're calling these things chlorine radicals. They're really chlorine atoms. So the terms can be used fairly loosely. So the termination steps kill the radicals. And we could go back with the other mechanism and try and write all the possible termination steps that it had. But since there were three different species of radicals that were formed, an OH, a Br dot, and an alkane dot, you would have many more different products. So, but same principle, just a different reaction. So this is 6 steps. And what would normally happen in this case is I would, number one, before an exam, I would ask you to do this as part of a graded practice problem. We'll probably do that next week. Ask you to go through the steps and the mechanisms to practice. But not today. So this mechanism and the more important parts of these mechanisms will be not on Monday's exam. It'll be on after that. But if I would have said that earlier, you would have immediately just tuned out. If you're already tuned out, then you didn't hear that. Because we are now in the last 2 weeks of classes. And when I first got here, Dr. Weaver said, they tune you out in the last 2 weeks. And I said, really? Really? I mean, he had been here 45 years, so he knew. But still, he's like, really? I said, I'm coming from OU. We were on 10-week classes. I mean, you can pretty much take a conservative guess as to what week they tuned me out down there. And particularly in those days. Those were the pre-scholarly days when the national holiday was Halloween. Well, I know, but it's less, but I think it's more scholarly now than it may have been in the past. Not that it wasn't bad, it's just, okay. So that's my 2-week notice, don't tune me out yet. Tune me out after the final exam. Right, because you don't want to be approaching the finishing line and end up, face down. This far from it. You want to quit when the quitting time is near. Okay, let me end with this. Our important part of this reaction is to say I give you something a little more complicated than methane. So I give you butane. It's not that complicated, but it's more complicated in the fact that now I can go through and I can write all the possible products that I could get from monochlorination. So again, I'm going to replace a hydrogen with a chlorine. If I replace a hydrogen with a chlorine on the first carbon, on the CH3 carbons, what am I going to make? I'm going to make product A, which is 1-chlorobutane. Now, I could replace any of those hydrogens, or I could replace any of those hydrogens on the CH. Any of the CH3 hydrogens gets replaced, I make 1-chlorobutane. That's product 1. If I replace any of the CH2 carbons, or any of the CH2 hydrogens with a chlorine, what do I make? I now make product B, which is going to be 2-chlorobutane. Okay, these are two different products. I know that because they have two different names. I now have two different products that's formed. My next question is going to be, what's the major product? And that's a complicated question, right? If I said, well, right, it is, right? What's the major product? It's complicated. What is it complicated by? Did I use chlorine or bromine? Will they give different major products? Oh, yes, they will. Did I use light or heat? Does that make a difference? Oh, yes, it does. So, which one is the major product is going to be complicated by the fact is what conditions did I use? Now, this isn't bad. It's not bad that I can make two different products by changing the conditions. Because after all, if I'm working at a chemical company and somebody says, hey, I need 2-chlorobutane, you can say, oh, well, I can adjust the conditions and make that for you. And then somebody else comes in and says, well, no, I need 1-chlorobutane. Okay, I can change the conditions. I can make 1-chlorobutane as the major product. The complication is, why? And so we're going to have to talk about Hammond's postulate again. But that's next week. Okay? All right, so I'll take your list of topics. I will create one for this evening. If you have any questions, put them on Piazza. I have a couple questions I need to answer. Otherwise, bring your questions on Friday and we will